Okay, so again, we can consider how far we can go with these sets of rules, and we showed that one big flat list that gets pretty complex might be hard to interpret. So one thing we might do is consider grouping redundant conditions, right? And so this starts to look like a program you might write in any language, where you say if the passenger's in first class, then if they're female, then survive equals yes, and if they're male and age less than 5, then survive equals yes or no or whatever. And if they're in second class, then have another nested set of conditions and so on. And so this starts to look like a tree, and these decision trees are what we're going to talk about next. All right. So how this looks, maybe diagrammatically, is this, right? You sort of drop each passenger down the tree, and each node in the tree makes a decision about where they go based on their attributes, and eventually you end up at a particular bucket. Okay. And so you can imagine here that which attributes you start with on top allows you to generate a lot of different kinds of trees, and they'll have different properties. Now, the relationship between one of these decision trees and the sets of rules is that every path from the root represents one rule. Okay, so you can always turning a tree into a set of rules is pretty trivial, because you just draw a line from the path to the root, draw a path from the root to the leaf, and every time you can do that, you end up generating one rule. Going the other direction is not necessarily straightforward, because there's redundant subtrees and so on. So you need to make some decisions about how to handle that. All right. So switching examples for a second, consider going back to this document classification example. You can build decision trees in this case as well. You can say, look, if the document includes the term Sunday, you either have yes or no, and if it includes the word saints, then you have yes or no, and if it does, then it's probably talking about sports, right? And if it includes the word Sunday, but it includes the word Mars, then it's probably talking about science. Okay. And so here, Sunday, the include Sunday yes or no condition being at the top maybe wasn't all that helpful, and we'll make that notion more precise in a moment. Okay, so in order to make a decision about whether a node in the decision tree is helpful or not, which I just claimed that we had an example where one wasn't helpful, we need this notion of entropy. Okay, and a way to think about this is consider two different sequences of coin flips. Okay, and we want to figure out how much information do we get after flipping the coin in each sequence once. All right. So the reason I'm talking about two different sequences is we want to have some kind of relationship between these two different coin flips. And so what we want to be true is that the probability of it coming up heads on the one hand and the probability of coming up heads on the other hand, with these two coins, we know that if those events are independent, which we assume they are, assuming everything's fair about these coins, then you can multiply those probabilities together. And so if we're trying to make up some new function called information, then we want information applied to the joint probability of those two events to be the same as the information gained from one of the events plus the information gained from the other event. Okay. So let me just say that again. We're doing an experiment with two different coins simultaneously, and we're trying to design a function that captures our intuition about what information is. Okay. And it must have this property, right? Any sensible definition of this information function must have the property that if I have two different separate events, I should be able to add their information together to get my total. And that should be the same value as applying the information function to the probability that they both happened. Okay, so with a fair coin flip, it's 0.5 times 0.5. So information of 0.25 ought to be the same as information of 0.5 plus the information of 0.5. Okay, and it's here on the slide. The function that gives you that is log base 2. Okay. Fine, so that's the information. Now, what's entropy? Well, entropy measures the amount of unpredictability in a set of events, a sequence of events. And so this is the expected value of the information. Okay, and expected value, whenever you see expected value, you should always be thinking about, I'm going to be multiplying a probability by a value gained if that event occurs. Okay. And so here you're saying, and then adding up all those eventualities. So that's all, expected value in every circumstance is going to be multiplying probabilities by values. And so here is no different. So we take, I pause because I see that there's a bug on this slide, which is, this is negative. Because log of a probability is less than 1, so that's always going to produce a negative number. And we want information to be a positive number, so we need to reverse the sign. And it's reflected down here, but it wasn't reflected in that definition. Okay, so we understand why information is the log function, and we understand that we want the expected value from a whole sequence of events. And so the formula falls out of it. It's the probability multiplied by the log of that same probability, and then add all those up. Okay, and so this guy comes up a lot. We're going to use it in one particular way, but you should keep your eye out for it. Whenever you see, some value from 0 to 1 multiplied by the logarithm of that same value, you're talking about entropy. So let's look at an example. So assume you're flipping a coin, and we see the same expression here on this slide that we saw on the last slide, except that this should say x instead of I. X or I is fine. It doesn't make any difference, but they should be the same. Then you expand this expression this way. If it's a fair coin, then you have 0.5 times the log of 0.5 plus 0.5 times the log of 0.5. This representing heads and this representing tails. Okay. And if you compute that, the answer is 1. And this is appropriate because we imagine that flipping a coin gives us exactly 1 bit of information. Right? It tells us the result of one 50-50 choice. Okay, so things are either on or they're off, and when you tell me the answer, I've learned 1 bit of information. All right, so now consider if we're rolling a die, there are 6 outcomes, each having a probability of 1 over 6. And so use the same expression, 1/6 times the log of 1/6, and add all those up, which is just multiplied by 6 in this case, and you get entropy of 2.58. Okay, so what this says is that when I roll a die and get the answer, I've learned more information. This is less predictable, more unpredictable, right? It's a higher number, more unpredictable than flipping a coin, which agrees with our intuition. All right. So now imagine rolling a weighted die that had these probabilities. Values 1 through 5 were all 10% chance, and it had a 50% chance of rolling a 6 every time. Well, we can do the same thing, and there's that bug again. This could be x. So this is 10% times the log of 10% times 5 plus 0.5 log 0.5. And so here you get 2.16. So here a weighted die is, goodness, less unpredictable than a fair die, right? Which again agrees with our intuition, right? Because if you had to bet what was going to come up, you would bet on that a 6 would be rolled. Okay. So how do you apply entropy to a data set as opposed to a random variable? Well, you can do it with respect to the class labels. So if you have 891 passengers in the Titanic data set and 342 of them survived, then you can compute entropy from those two sets. So 342 over 891 log 342 over 891 plus 549 over 891 and so on gives you an entropy of 0.96. So this is almost 1 bit of information. And this makes sense because 342 is about half of 891, right? So it's about, you learned a lot by identifying someone as having lived or died, okay? But then say there were only 50 survivors. Well, then The data set is inherently more predictable, right? Because most people did not survive, and that's reflected in this calculation. You get an entropy value of 0.31, so it's inherently less unpredictable or more predictable. Okay. So fine. So that's entropy. Going back to decision trees. Now, which attribute do we want to choose at each level? Right? We're gonna build a tree, and we have to make a choice of which attribute we're going to use to split on. Okay, and the one we're going to pick is the one with the highest information gain, and we're going to use entropy to compute information gain. And another way of saying that is it's the one that reduces the unpredictability the most.